Hello everyone, welcome to today's lecture. In this lecture we are going to start with micro operations. So let's start. So the operations executed on data stored in registers are called the micro operations. In our previous lecture we have seen what is a micro operation is. Yes, that micro operation means the data that is stored in the registers and we are performing some operations on that, and that is called the micro operation. Suppose we want to add the data of two registers. For that we are using some arithmetic micro operations. Suppose we want to shift the bits in the registers, so at that time we are using shift operators. Yes, so all that types of operations that we are performing on the data, that is called micro operations. A micro operation is an elementary operation performed on the information stored in one or more registers. So for example, shift, count, clear and loads. So these are some of the examples of the micro operations. Now there are mainly four types of micro operations available. So the first is register transfer micro operations, then arithmetic micro operations, then logic micro operations, and the fourth one is a shift micro operations. So the first is a register transfer micro operation that we have already discussed in our previous lectures, that how data is transferred from one register to another registers. So we'll start with the arithmetic micro operations. So the arithmetic micro operations provide some basic operations like addition, subtractions, increment, decrement. Yes. So the first is add micro operation. So it is defined by the following statement, which is we are adding the data of R1 and R2. So R1 plus R2 and then replacement operator, and we are storing the result into the register R3. So this is how we can show the addition operation in the form of symbols. So the above statement instruct the data or the content of the register R1 to be added to the data or content of register R2, and some should be transferred to the register R3. Okay, same as suppose I want to subtract some data of register R2 from register R1, then we'll write as R1 minus R2. But when we are actually implementing on the computer system, so at that time it cannot be possible directly. So for that we have to calculate one's complement of register and then we'll add 1 into it. Suppose in this figure you can see that so data of register R2 is subtracted from register R1. Okay, so we can write this statement like R1 then plus R2's complement, means the one's complement of R2 plus 1. So this is how the actual statement is executed, that first it calculate the one's complement of R2, then add 1, and then the result of this is added into the register R1. So this is how we can calculate the subtraction. So in subtract micro operation, instead of using minus operator, we take one's complement and add 1 to the register which gets subtracted. So R1 minus R2 is equivalent to R1 plus R2's complement plus 1 and then replacement operator, and the result of this operation is transferred into the register R3. The third one is increment and decrement micro operation. Suppose I want to increment data by 1 or I want to decrement data by 1. So for that this types of micro operation is executed. Increment and decrement micro operations are generally performed by adding and subtracting 1, 2 and from the registers respectively, and this is shown like R1 plus 1 and R1 minus 1. Okay, so these are the details of each and every operations, like R1 plus R2 means the content of R1 plus R2 and it is transferred into the R3. Same as for minus. Then here R2 and R2 bar. So R2 bar means the complement of the content and the complement means one's complement. Some number is positive, yes, and you want to negate that number. So for that R2 bar plus 1 means 2's complement of the content. Then subtraction, as I said, that R1 minus R2 is written as R1 plus R2 bar plus 1, and increment means by plus 1 and decrement is decrement by minus 1. Okay. Now in this lecture we are going to implement the adder, how we can add the two binary numbers. Okay, So suppose we will start with the first operation. So this first is a R1 plus R2, and then it is moved on to the register R3. So we'll implement this first. So for that, the binary adder is used. So the digital circuit that generates the arithmetic sum of two binary numbers of any length is called the binary adder. So suppose we have two registers, and the register 1 contains 1101 and the register 2 contains 0, 1, 1 and 1. Okay, so these are the two data. Suppose I want to add these two numbers. So for that we are using a full adder. Okay, so full adder requires three inputs: the input of register A, input of register B and some carry input. This three input is given to the full adder and it generates the sum as well as carry. And why we are using full adder rather than half adder? So the full adder is used when we want to add more than 3 binary bits. So here first we are adding this 2 binary bits and it generates 1 plus 1. The addition of 2 binary number, 1 plus 1 is equals to 1, 0. Okay. So 0 is the output, so it is written here, and the 1 is a carry bit. So this carry bit is moved onto the top. Now this is a 3 binary bits. We are adding this 3 binary bits, 1, 0, 1. Because we are adding this 3 binary bits, that is why we are using full adders. So this is the basic concept, that what types of adder we are using for the addition. So now it is clear that we are using full adders. Full adder requires 3 inputs. First is a register A, register B and the carry inputs. So let's understand how it is implemented. Suppose I want to add this two binary number 1101 and 0111. So for that, this is the circuit diagram of the binary adder. Here we are using 4 full adders. Now the question is, why we are using 4 full adders? Because here you can see that register 1 contains 4 bits, 1101. Register 2 also contains 4 bits, 0111. So because we are adding 4 bits, that is why we are using 4 full adders. Okay, so that one thing needs to be remembered, that number of full adders required is equals to number of bits in the register. So this circuit diagram, this implementation is called the 4-bit binary adders, because we are adding 4 bits. Suppose you are adding 8-bit binary numbers. So at that time you required 8 full adders, and that implementation is called 8-bit binary adders. So I hope now this is clear. As I said that full adder requires 3 inputs: the data of register A, the data of register B and carry input. So here you can see that full adder has a 2 input: the data of register A, the data of register B and the carry. So what is the data of register A and register B? Now A is equals to 1 1 0 1, B is equals to 0 1 1 and 1. Okay, now this is the first full adder. We required the A0 input of first register. So the input of the first register will calculate from right to left. Okay, so the first bit is a 1, so we are giving A0 as a 1. Same as the second input is given to the second full adder, so it is 0. Okay, second bit is a 0, so the 0 is given as A1. The third bit is given to the third full adder, so it is 1, and the fourth bit is given to the fourth full adder. Okay, so the number is become 1 0 1 1. Same as we are giving the input of register B. So the first bit of register B is 1, so B0 equals to 1. Then the second bit of register 1 is 1, so the B1 equals to 1. Third bit is also 1, so here B2 is equals to 1, and the fourth bit is 0. That is why B3 equals to 0. Okay, so this is how we are giving the inputs to the full adders. Now how it is performed? So it requires carry inputs. Okay, so here we are providing carry input C0 as a 0. Why? Because suppose you are adding 3 plus 2. Okay, so it generates output 5. Okay, now if you are adding carry input 1, so the output may be changed, because the right output is 5 but you will get the output 6. Yes, so that is why we are not giving the carry input as a 1, but we are providing carry input as 0, so the result cannot be affected. So first input is 1 1 and carry bit as a 0. Okay, so now let's start calculating. So the first bit A0 is equals to 1, B0 equals to 1, and carry input is a 0. So this is a full adder, so it adds these two binary bits and generates the output. Now we all know 1 plus 1 means 1 0. Okay, so the output is 0 and the carry bit is 1. So here S0 is the output, so it generates 0 as output, and the carry bit 1 is given to the next full adder. Here 1 is a carry bit, so this carry bit is given to the next full adder. Okay, now here the carry bit is 1, input of register A1 A is 0, input of register B is 1, so the number is become 0 because the first bit of A1 is 0 and then 1 and then carry bit 1. So we'll add these numbers and it also generates the output 1 0. So the S1 is the output variable, so it stores 0, and the 1 is a carry bit. This is given to the next full adder. Now next full adder has the value 1 1 and 1. So 1 1, value of A is 1, value of B is 1, and the value of carry is 1. And the full adder adds these numbers and generates the output. Now 1 plus 1 plus 1 is equals to 1 1. So it stores 1 as a output. So output variable S2 stores 1, and the remaining 1 is a carry number. So this carry number is forwarded to the next full adder. Now the next full adder has 2 bits, which is value of register A is 1, value of register B is 0, and the carry bit is 1. We'll add these numbers, so it generates the output 1 0. So output variable S3 stores the 0 and the carry 1 is generated. So this is how the 4-bit binary adder works. Now you can see in this figure, at the end it generates some sum and the carry bits. Now the sum value is 0 0 1 0. Sum value is 0 0 1 0. Okay, 0 0 1 0, and the carry bit is 1. So in this figure here the carry bit is 1. So this is how the addition is performed onto the full adders. So this is how with the help of full adder we can add any binary numbers. So I hope now this is clear that how the binary addition is performed. Here 1101 is the binary number and the decimal of this is 13, and 0111 and the decimal of this is 7, and at the end it generates 10100 and the decimal of this is 20. So this is a simple addition, and this is a binary addition of these numbers. Now next is the explanation that I explained. So the AND binary adder requires AND full adders. Yes, so as I said that suppose you want to add n bit binary numbers, at that time you requires AND full adders. The output carry from each full adder is connected to the input carry of the next high order full adder. So the statement said that the output carry of this full adder is given to the input of the second full adder. The n data bits for the A inputs comes from the one register R1, and the n data bits for the B comes from the another register R2, and the sum can be transferred to the third register or the one of the source register R1 or R2 or replacing its previous content. So the output, now this sum is stored onto the another register. So the binary adder is constructed with the full adder circuits connected in cascades, means in the sequence, with the output carry from one full adder connected to the input carry of the next full adder. The figure shows the interconnection of 4 full adders to provide a 4-bit binary adder. So the first So the bits of A and bits of B are added from right to left, that I already told, that bits of A and bits of B is added into the full adder in the direction of right to left. The carries are connected in a chain through the full adders. The input carry to the binary adder is C0 and the output carry is 40. So when we provide carry in the first full adder, then it is C0 and the final output carry is a C4. Suppose it is a n-bit binary adder, so at that time first carry bit is C0 and the last carry bit is Cn. And the S is the output of the full adders, generates the required sum bits, and the final S bit, so S is equals to 0 1 0 0. So this is the final output. So this is all about the 4-bit binary adders. I hope now this is cleared. Thank you so much for watching this video.